Okay, last of the 108 modules today. Modules, sessions. Covering dynamic programming. That was not what I wanted to do. There we go. I don't know why that moved to the screen. Yep, so dynamic programming is an optimization method. It's also a paradigm of a sort, but for our purposes, we're just looking at it as an optimization method. So optimizes that's good enough. Optimizes recursive algorithms. So the things that we were creating yesterday with divide and conquer, this dynamic programming is all about making those more efficient. It does so via caching and also by using an iterative approach. So it is all about refactoring recursive algorithms into using iteration rather than recursion, and also by caching values so you're not redoing the same process repeatedly. And the reason why these two are useful, especially caching at first, can be seen by looking at a recursive algorithm to compute the Fibonacci numbers. So if we have some function that is huge, got to reset my pen size. I think green's the same. Yes. So if we have some function f, calculate Fibonacci, it takes in an n, then we can define this more formally like so. It will return a 1 if n is equal to 1 or 0. Perhaps I should actually line this up properly. There we go. And otherwise, it will return f of n minus 1 plus f of n minus 2 if n is more than 1. And if you were to draw this graph out, say we were looking at f of 6, so we're trying to find the 6th Fibonacci number. In that case, we will be looking at f of 6, I'll just do it in subscript. And to do this, it doesn't fall into our unit case or our stop condition, so we're going to be doing recursion. We'll be looking at f1, so f of 5, as well as f of 4. Actually, align my notes to what I'm looking at. There we go. Again, 5, not a stop condition, it's going to be going down as well. So we'll be looking at 4 and 3. Each of these will be going further. I didn't draw a line. F of 4 will also be doing f of 3, as well as f of 2. F of 2 will be going down to f of 1 and f of 0. F of 3 will be going down to f of 2 and f of 1. F of 1 and f of 0 being our stop condition, so that won't be recursing any further. So we're going down to f of 2, which will then also go down to 0, 1 and 0. This is the issue of drawing trees. Now it's crashed into itself. F3, this is an f of 3. F of 3 will be splitting into the same thing as over here. So f of 1, then also f of 2, going to f of 1 and f of 0. That's between them. F of 4 will be going down to f of 3. Same thing as this entire half of the tree we repeated here. So f of 3. In fact, rather than draw it out again, imagine all of this here. So the tree is not very efficient. You can see here we have f of 6, f of 5, f of 4 here, f of 4 here, 3 here, 3 here. There'll be another 3 at the end of f of 4. So generally not very efficient. We're repeating ourselves all the time, and that's not good. What we want is to be able to make that less repetitive. In computer science, we don't want to be repeating ourselves. That's a bad thing. So the idea here is we just cache. When we compute a value, we'll store the result. So if we need that value again, rather than recompute the entire thing, we can just say, oh, we've already calculated this. Let's take the value there that we've already stored. So that can be done, for example, by producing a table like an array. And then whenever you want to look at, for example, f of 3, you would look at the f of 3 cell of the table and say f of 3, oh, that's this number. Rather than do all of this down here, we're just going to return that number. So we're adding a new stop condition, essentially, where as well as if n is less than 1, you also have and not yet computed. If it has been computed, so if n is less than 1 and has been computed, then we just return that value in the table. So return table of n. The nth position being the thing we've already calculated. If I do that square brackets. With that, you can see it's become much more efficient in terms of how many times we're going to be calling functions, because we're trimming the tree. The tree looked like this. If you were to actually do it, what you'd get is calling f of 6, because we haven't got that in the table anywhere. That's what we're trying to calculate. If we had it in the table, we wouldn't be calling it. That'll have to go down to f of 4. And let's say we'll go left first, actually, for simplicity. So we'll call f of 5. We'll calculate f of 5. F of 5 will have to calculate f of 4. So now we have a table of f of 6, f of 5, f of 4. That has to go down to f of 3, f of 2, f of 1, f of 0. Lie between those. So now we know the value of f of 2. So that's stored in the table. F of 3 has to have that plus f of 1. F of 1 will also be in the table, because you might as well put it in there. So now f of 3 is in the table, f of 4 is in the table. Once we add in f of 2, f of 5 when we add in f of 3. We don't need to be going down this branch because we already know it. Same with f of 2, we don't need to go because we've already stored it. So these values are already in the table. We don't need to redo all that branch, all those subtrees. Same with f of 4. Rather than doing all of this, which is the entirety of this half of the tree, again, we can look in the table and much more efficient. So through that, we can see that is a much more efficient way of doing this computation, because the number of functions we have to go into is dramatically reduced. However, it's still not perfect. We can improve this further if we're in a situation where we need a lot of efficiency, or we need to be as fast as possible, with as little impact on memory and all the rest. Then it's in fact better to avoid function calls, because function calls have overhead. Every time you call a function, there's stuff the computer has to do. That's the type of thing covered by 124. You want to put a stack frame on the stack representing that function. Every time you have another call, it's another stack frame, tons of setup when you exit. It's a ton of stuff to take it down. It's a ton of extra stuff you have to do. That generally is going to be adding a bunch of extra stuff that is not actually contributing to your program and solving your problem. So we can rewrite this as a for loop. That doesn't have any functions in it. It's a single function call, which is the thing that has the algorithm in. And it will calculate it for us. And we can do that by calculating bottom up. Whereas normally if you want f of 6, if we know it's f of 5 plus f of 4, if we were to calculate the other way around, from f of 1, f of 0, all the way upwards, to f of 6, that's our limit, then we could. That's the idea. That's the other part of dynamic programming. First is to limit the number of repeats by caching the stuff you already calculated. And the second is to refactor in some way so that you can calculate it via a for loop instead. So the idea would be that we would calculate through it, and I'll be demonstrating that for loop, not in code but in practice, in the next section, which is about the assembly line problem. And there. So this problem, if we have some graph like this that represents an assembly line, items will start at the start position and go to one of the two sides of the belt. It costs the amount of time in the circle to be processed at that station, and then it has a choice. You can either continue on that side of the belt for no cost, or it can cross the belt and then be processed on the other side. And the idea is we want to find, for any arbitrarily given node, what is the fastest path an item could take to get to that node. For example, here, what's the fastest way we can get to S12? Either is it going to S21 first and crossing over, or is it going here? And you can see it will cost 3 to get to here, an extra 3 to get to here, and then a 5, whereas here it's just 3 and 5. So this would be the quicker path to get to S12. You could do this recursively, if you see, because the cost to get to any particular node is the minimum. Let me just change color. Is the minimum. So we have some function min, which returns the smallest of two given arguments, of the cost. So C is a function. C is a function which will be representing the cost of a node. This is our recursive function. The cost of some node in an array S at position I and J minus 1, because we want to look at it. We're looking here, we want to look at the cost of this node plus this, and also the cost of this node plus this. And this is always 0, this is always 0, so we only need to add on when we're crossing. So that's our first cost, and our second cost is the cost of going to this path, going to this node first and then crossing over, which would be C. That looks like it would be C of S, then it's I minus 1, and then J minus 1. And of course, you have to be adding whatever the swap cost is. So plus a swap cost. In this case, it'll be 3, 1 here, 2 here, 1, 3, 4. So whichever that is, that's appropriate. So that would be the method of finding recursively the cost of any single thing, because then you would call it for this, recall it for this, go down all the way, and you're going to hit the same problem where, for example, to find the cost of this one, you're going to have to find the cost at this position. But to find the cost of this position, you're going to need both of these. You need, for example, S2 of 2. But in order to calculate this one, you'd also need S2 of 2, and you need both of these to find it. So you're going to be calculating S2 of 2 twice. That's not very good. Dynamic programming says we can do better by trying to cache those values, and also by using a bottom-up approach. Essentially, we want to be calculating this one, then this one, this one, then this one, and then this one, then this one, in that order, so that we can build up from the bottom to the value using everything as few times as possible, all on a for loop, so we're not using any overhead from calling functions. 1 moment. Okay. So the process behind this, if we have, for example, S of 1, we're starting here. The cost of this is just 3. You can see there's no cost to start. So 1 of our 1 is 3. 1 of 2 is 3 as well. To get to 5, it's S1, 2. That would be this one. 1, 2, and then 2, 2 is this one. To get to 1, 2, is either 3 add 5 being 8. So it's either 8 or it is 3 add 3 is 6 add 5. Now clearly 8 is the smallest there, so this one is 8. For this one, it is either 3 add 2 or it's 3 add 4 add 2. Again, clearly 5. And we don't have to be recalculating it. That's the whole point. By doing this in a for loop where we can iteratively go over each, we can iterate over each of these, we're able to much better fill out this table in only one pass, just by searching what the values we've already computed and then stored. For this one is next. That is either the cost of this one or the cost of this one. The smallest of those two would be 8 plus 0 or 5 plus 1. 5 plus 1 is smallest, so this one is a 6. For this one, it would be either 5 plus 0 or 8 plus 1. So 5. And then for the last one, it's going to be either 6 plus 0 or 5 plus 3. So this one's 6. And then this one is either 6 plus 2 or 4 plus 3. So 4. Now I realize I forgot to take up the answers of these. So at the end, I'll have a quick look to make sure I haven't messed up the math there, because that's very easy to do with these live type of things. Did I, for example, it seems I've forgotten to add a 4 somewhere. Which number is that? Is that 1, 4? Or is this one? 1, 3. Oh, yes, I didn't add the 4. Oops. It'll be 10 because it's the 6 at the 4. And then for this one, that will recalculate these two, so I'm actually going to have to redo these. For 1, 4, then it's either 10 plus 0 or it's 4 plus 3 is 7. This one would be 7, and then this one would be it would be either 10 plus 2 is 12 or 5 plus that. Yeah. That'll be 5. That doesn't look right. Have I forgotten to add something somewhere? 2 or 4 is this one. It's either this one, which you said is 10, plus 2 is 12. We don't want that, that's too much. Because this one, which is 5, would be 10 as well. Oops, that's why. And so, for example, also what we've got here is if we wanted to get to the end, so just what's the shortest path through this assembly line, we can go through each layer and say, okay, this one, well, 4's the best, 1, 4, because it only costs 7 to get here. Then we can go all the way back down. Then 5's the best here, and then that all the way down. So through that, we can calculate what is the shortest path for each of them, and then work our way back down and find the shortest path through. And that will be a iterative approach. Other way would require calculating the same thing a ton of times. And that's really all dynamic programming is. It is just the concept of here's a recursive algorithm, rewrite it as a for loop, and cache things so you're not recalculating needlessly. Prudence spent about an hour and a half on it, and I honestly don't know why. But yes, I did forget to add the value of the node.
Are there any more examples anywhere?
No. Well, there might be some. I haven't looked at the example questions. This was from the tutorial, but it's also in the video.
Okay.
Honestly, I think this is the most complex going to get. We don't have to care about
Oh.
recurrence in terms of
Mhm.
exam. We do have to know it. We don't have to care for the exam.
Yeah.
So this is, I think, as hard as it's going to get, and it is just a process of follow along and figure out which one is the smallest. Given any arbitrary one, work out up to that. So this one, this one, this one, this one, then calculate this one based on the rest. Like for the tutorial, the question was, what was it? Find the shortest route through. Find the shortest path to a single one. I think with the 2 questions on it. It wasn't particularly complicated. And I messed it up because it's difficult to do mental maths on the fly while also presenting one of these.
All right. Thanks.
Yeah, very short one this week. Again, I keep saying week. This session. In fact, I shall see if I can find my solution to the tutorial. Da, 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 da. have it anywhere. Yeah, I think that's right. The method's certainly right. I probably just, if I did get it wrong, it's because I added something wrong somewhere. But that the approach is the correct one of go through and calculate and just add and take the minimum. If there's no other questions, then we're done for today. This was a very short one.
Thank you.
Yeah, top man there. No
Oh my
questions
god.
from me.